All right, there was a question about this problem from the homework, so I wanted to just show you how I would go about solving it. And so let's go. So this question says we have a spaceship leaving Earth's orbit and it's heading to the moon. It has an acceleration of 20 meters per second squared. The time that it's accelerating is 2 minutes. And during that time, it covers a distance of 1,000 kilometers. So, and notice this I wrote as a distance between where it ends up and where it started. But we could actually say that x naught is 0, and then that would make it easier. But in any case, the first thing I wanted to mention is units here of the information that's been given to me isn't in the units that we would want to use. In our problems, we're going to always be using what we call the MKS system, which is meters, kilograms, and seconds. So the idea here is these are the basic units that all other units would be based on. So length we always measure in meters, mass is always going to be measured in kilograms, and time is always going to be measured in seconds. So using that, my time, I have to convert to seconds. So I use the fact that 1 minute is 60 seconds, and so our time we should use is 120 seconds. And then our final position, which is 1,000 kilometers, we use the fact that a kilometer is 1,000 meters. And so this gives us 1 followed by 6 zeros. 1, 2, 3. And so scientific notation makes it a lot easier. So it's 1 times 10 to the 6 meters. So we have that. Now, the question is we want to know the initial and final velocities, of the spaceship. So we want to know the initial and just v. So let's go to the next slide so we have more room. So I have 2 kinematic equations. These are the equations we derived in class today. X equals x naught plus v naught t plus 1/2 at squared, and v is equal to v naught plus at. So I'm going to highlight the information I have. I know what x is. I know what x naught is. I know what my time is. I know what my acceleration is. So that's known in acceleration and time. So the things that I highlighted are the things that we know. But you can see that neither one of these equations on their own is going to allow us to solve the problem. But we can use them together because in the end, we have 2 unknowns that we're looking for, the initial velocity and the final velocity. So what I'm going to do is I'm going to put in our known information. So for instance, here in the x expression, the total distance or the final position of the rocket was 1 times 10 to the 6 meters away from where it started. Our x naught was 0. We don't know what v naught is, but our time is 120 seconds. And then 1/2, our acceleration was 20 meters per second squared, and then 120 seconds squared. So this gives us 1 times 10 to the 6 is equal to 120 v naught plus 1.44 times 10 to the 5th. And so we can actually solve v naught, 120 v naught is equal to 1 times 10 to the 6 minus 1.44 times 10 to the 5th. V naught is equal to 1 times 10 to the 6 minus 1.44 times 10 to the 5th divided by 120. And so we find a V naught of 7,133 meters per second. So that's one of our answers. Now that we know that, we can use our other expression, V is equal to V naught plus AT. And so we know that our V naught is 7,133 meters per second plus our acceleration, which is 20, times our time, which is 120 seconds. And this gives us a final velocity of 9,533 meters per second. And that is how we can solve that problem.